Hello, my name is Fabio Tabaco, and I will present my work titled Theoretical and Experimental Study of Supersonic Gas Jet Targets for Laser Wakefield Acceleration. So first of all, I will make a previous introduction for this work. The use of the laser wakefield accelerator systems has grown rapidly in the scientific community as a new technology of particle accelerator systems. So it reduces the size and the complexity and consequently the costs of particle accelerators. Moreover, in this type of acceleration systems, usually renewables fluid targets are used to create a plasma and stimulate the generations of a longitudinal electric field capable of accelerating electron. The nozzles that can accelerate the gas jet in a supersonic flow is this kind of jet of nozzles that is named or is called by the Laval nozzles. So it's a convergent and divergent nozzles that can accelerate the flow. So PT and whole is the pressure, temperature, and density of the backing chamber of this side. And this side is the same characteristics of the flow of the fluid and the experimental chamber. That in our case is the vacuum chamber. So here is the trough radius, and here is the exit of the nozzle radius. So in our case, we built these nozzles, and we compare, and they are compared to a theoretical analysis made with a computational fluid dynamic simulation with a finite element method. So the software used for the simulation is named ANSYS, version 19 academic. A simple quasi 1D model can estimate the gas jet Mach number based only on the radius of the exits and the trough area and the type of the gas or the gas. This model disregards characteristics for some characteristics, for example, the exact background pressure into which the jet expands and the nozzle length. To better understand and design the nozzles, the numerical simulations used by us in this work are needed. So now we'll talk about the methodology used in our work. For the experimental results, we assembled a Mach-Zehnder interferometer with a Schillering imaging to characterize the profile and the gas density in the jets generated by the homemade nozzle. The interferometer is here represented, and we have helium-neon laser that have a beam, and it's splitted here in this beam splitter. One arm passes through the gas jet, and an image formed here in this surface of the CCD. So the computational fluid, here we can we put one lens 12 centimeters away of the gas jet that formed an image 5 times of magnitude of the original, of the real image. Um, the jet's positioned inside a small vacuum chamber with Brewster windows, and the backend pressure in the gas net is up to 550 bar, and the residual vacuum chamber is about 20 millibar. So the simulation is used to understand the flow and the phenomena that can happen when the gas is forced through a homemade level nozzle. In this work, we simulated an etched nozzle and an aluminum plate by an ultra-short pulse machining system in our lab. So the diameter is about 190 of the exit, and the throat is about 86 micrometers of diameter. It defines a Mach number about 3. According to this quasi one-dimension model, and more details of this manufacture nozzle can be seen in the work of Bruno Chiometto, titled "Develop of the level nozzles for laser electron acceleration by an ultra-short pulse micromachining." And this work will be present in this conference. The fluid used is ideal N2 in a CFX model of ANSYS, and the gas flow is described by a Navier-Stokes equation. The backend pressure simulated is 50 bar on background pressure, and the background pressure is determined with an exhaust pressure of 20 millibar. So in the results session, we divide in experimental and theoretical, theoretical, and the comparison between them. In the experimental analysis, this figure presents the interferogram image acquired by the CCD, by our CCD, and this right figure shows the density map derived from them. After applying mathematical methods from the density map, here we can measure the divergence angle of the gas jet. So it's about 20 degrees. Here we can see it. So according to the 1D model, the Mach number is 2.8. It's about 2.8. The work presented by Armando Zuffi, titled "Development of a Modified Mach-Zehnder Interferometer for Time and Space Density Measurement for Laser Wakefield Acceleration," is possible to verify with more details the process to acquire this kind of density map from the images of the interferometer. So about the theoretical analysis, as already told, the nozzle has the same diameter and length as this experimental, and we consider that its walls has low hardness. So in these figures shows the molecular density distribution of the gas in orthogonal planes. And this one, and those one, it can be seen an abrupt density change and that is desired for laser wakefield acceleration. In this figure, we can see the circular section, transversal section of the gas jet. The density decrease along the nozzle as the gas jet grows, and the minimum value is reached at the exit of the nozzle. Here, here. Some inhomogeneities in this figure are simulation artifacts because of a non-ideal discretization of the space due to an academic license that has a limitation of the maximum number of nodes and elements of the grid. So this characteristics results in a simulation that does not describe exactly the physical system. So in this figure, we have a Mach number distribution, and the maximum value occurs here near the exit of the nozzle, and it's about 2.5. The discrepancy between the theoretical and experimental results are about the simplified one model that disregards some factors, some real factors, for example, the length and the shape of the nozzles. So I told that the number of the elements influence the spatial resolution because it influences the size of the elements. Comparing the experimental results, theoretical, it's possible to verify that the simulations describe the behavior of the gas jet closely, mostly the Mach number and the density, the density near the exit, near the nozzle exits, about 100 micrometers. Although the experimental jet is more divergent than the theoretical one. So we conclude in this work that the simulated model describes the experimental results of the jet flows fairly close, but more studies need to be improved to get more realistic prediction and to design better nozzles and gas jet targets. So with the knowledge that we acquire in this study, it's possible to perform simulations of more complex systems. I will thank the financial support for PASP, CNPq, CAPS, and the CNPq scholarships to Zufi and for me. Thank you.